Today I'm going to talk about monitor calibration, how to ensure that you're seeing accurate colors on your monitor, and how to guarantee accurate color between what you see on screen and what you see in print. One of the most common issues that I run into with students when they're working digitally is they ask me why it is that their artwork looks perfectly fine on one monitor, on one computer when they're creating the artwork, but then they move that exact same digital file to another computer and the artwork looks completely different, and they're disappointed with the way it appears on another computer, another monitor. And similarly, they have the same concern about when they go to print their work. They produce a piece of artwork that looks great on screen, but then when they go to print it, the colors in the print don't at all match what they saw on screen. A lot of this relates to a kind of a strange idea in the world of computer graphics, and that is understanding what is reality in computer graphics. What component of a digital image is actually real? Is it what you're seeing on screen? Is it what you see when you print the file? I mean, what is the real digital image? One thing to keep in mind is that when you're creating a digital file, what you're doing is you're using some kind of input device to save bits of data into the computer. Remember that bits of data are just strings of ones and zeros that are used to define the RGB values for the color of an object. So when you're using your Wacom tablet to paint in Photoshop or something, all you're doing is simply changing the numerical color values of the pixels in a raster image. So you're simply saving data to a digital file. When you view that file on your computer's monitor, what's happening is that the computer is translating those ones and zeros, those numerical color values, into voltage. That voltage is then transmitted to the monitor to make colors and images appear on screen. So what's happening when you view something on screen is that you're translating the numerical values of that digital file into an image that's on screen. Now, unfortunately, every monitor is a little different. Monitors manufactured by different companies behave a little bit differently. Even different models of monitor made by the same company may behave a little differently. In fact, even two monitors of the identical model made by the exact same company may look a little bit different from one another. Even a single monitor over the course of its lifespan may change. Monitors actually change with age. In fact, even in the course of a day, a monitor may display color a little bit differently when you first turn it on versus after it's warmed up for half an hour or an hour. So there's tremendous variation in the way that a monitor will display the exact same numerical values in that digital file. The same thing happens when you print a file. You're taking the numerical values that are stored in the digital file, translating that into percentages of ink or toner that is applied to a sheet of paper. And of course, all printers are different, just like all monitors are different. Different brands of printers are different. There are many different technologies, such as inkjet or toner. There's also the offset press that's used for most professional printing. Each of these technologies is very different. So a given digital file may look very, very differently when it's printed to these different kinds of printers. And furthermore, just to complicate matters, the image that you print, again, could look different on different printers, but it may also not match what you saw on screen at the moment that you created the file originally. So just to summarize, every time you view an image on screen, or every time you print that image, you're seeing just an interpretation of the numerical values that are stored in that digital graphics file. So it turns out that the only thing that is real in a digital file, the only thing that is consistent when you copy that file and move it from one computer to another, to another computer are the numbers that are stored in that digital file, the numerical values of RGB that are stored in that digital file. That's the only thing that's consistent when you move that file from one computer to another, when you display it on different monitors or print it to different printers. So when you create an image on one computer and then you move the image to another computer and it looks very different on another screen, people are often tempted to blame the second computer. They assume that when they were creating the artwork in the first place, that they were creating a beautiful image because it looked great at the moment that they were creating it. They move that to a second computer and it displays very differently on the second computer. It's just human nature, I guess, to blame the second computer and say that it's not working properly. But of course, the reality is that it may be that the first computer that you created it on was not properly calibrated, that the colors that were displayed on that first computer screen were not accurate. It may be that you were saving, in a sense, ugly colors into your digital file. And then when you move that file to another computer, it may be that the second computer was actually showing you a more accurate representation of the ugly colors that you had created. The same thing is true with printing. So again, you create an image that looks beautiful on screen, you print the image, and the print looks terrible. How do you know if it was the image on screen that was inaccurate or if it's actually the print that is inaccurate? It may turn out that the print is actually an accurate representation of the numerical values that you created in that file, and it's just that the monitor on the computer that you were working on initially was not displaying the colors properly. Now, it turns out that this idea of what's real and what's not real was much less of a problem back in the old days of reproducing traditional artwork. Back when all artwork had to be produced using traditional media, there was always a real image that you could consult to determine if the colors that you were seeing later on in the reproduction process, the printing process, if those colors were an accurate reflection of the colors of the real image. So here's a little graphic that tries to describe what I'm talking about here. So imagine that you had an original painting, an oil painting or a watercolor painting. At every step in the process of reproducing that painting, you could always refer back to the original to make sure that you were matching the colors of that original painting. This could also apply to any kind of object. You could have a sculpture, you could have an article of clothing produced by a clothing designer, and they were trying to produce a catalog to sell their clothing. They could always refer back to the original article of clothing to see if the prints that they were producing were accurate representations of that color. So the way that this worked back in the old traditional printing process was that you would take that original image and you would somehow photograph it or scan it and produce a series of film negatives. We talked about this process earlier in the course when we were describing the digital printing of color, or the reproduction of color images in print form, is you'd have to make a series of 4 film negatives that corresponded to the 4 colors of ink used in the color printing process. So you take your original photo or your original article of clothing, your original object, you photograph it 4 times to produce a set of film negatives. Now, after the negatives have been produced, you could use those film negatives to produce something known as a contact proof. This was a type of print that was actually generated directly from the 4 pieces of film corresponding to the 4 colors of ink, cyan, magenta, yellow, and black. Back when I first started in this business, I was very fortunate to work at a company that could produce a type of contact proof known as a match print. And this was considered the gold standard back in those days. It was the best type of print that you could make that would show what that image was going to look like when it was actually printed on an offset press, because the print was literally created from the same pieces of film that would ultimately be used to create the printing plates to go on the offset press. So you could take this contact proof, such as the match print that I just described, and you could compare it back to the original image or the original object that had been photographed. And if you noticed that your proof didn't look exactly like the original image, there were methods that you could use. There were analog methods that could be done with photography to make slight modifications to the colors on these film negatives. Eventually, once you were satisfied that the film negatives and the contact proof made from those negatives was a good match to the original image, then you would take those film negatives, you would use them to burn a set of printing plates. Those plates would then be placed onto the rollers on an offset press, and they would print the four colors of ink, the cyan, magenta, yellow, and ink, onto paper to create the finished printed image. But even at that stage, you could take the prints that were coming out of that offset press and you could hold them right up next to the original piece of artwork or the original object that was photographed, and you could compare whether the colors were a perfect match with the actual original image or not. And a good press operator could actually make slight adjustments on the press to change the colors ever so slightly to change the printed image. They could choose to run any of the four colors of ink a little heavier or a little bit lighter to make little tweaks to the colors of the image. So in the traditional process, you could always compare your proof or your finished printed image back to the original. So in those days, the thing that was real was the original image, and you could always compare something back to that. But then in the 1980s, with the desktop publishing revolution, all of that changed. People started creating artwork from scratch using digital software, such as Photoshop or Illustrator. In which case, there was never a real image to compare your proof or your final printed image to. What you were doing was you were using a mouse or a Wacom tablet or some other input device to create your image. And remember what I mentioned before, that the image you were creating was nothing but a string of ones and zeros stored in a digital file to represent the RGB values of the colors you were creating. And as you were creating that digital image, the only feedback that you had was what you saw on screen. You weren't really creating the image on the screen. You were simply saving numbers into a digital file, and the screen was attempting to show you what those colors actually looked like. But you never really knew for sure if what you were seeing on screen matched the numbers that you were saving in that digital file. So later on, when you were thinking about generating print of this digital file, you could send it to various kinds of printing technologies. You could send it to a desktop printer like an inkjet or a laserjet printer, and you could generate a print. And I suppose you could take that print and you could hold it up next to the computer screen to see if the print matched what was seen on the computer screen. But again, you never knew if the print matched the numbers in the digital file. You never knew if what you saw on screen matched what was in the digital file. When it came to actually printing this thing on the press, you would take the digital file, you would send that digital image to either an image setter or a plate setter, which would produce the printing plates that would go on the offset press. And you would then print it on an offset press using the four colors of ink, CMYK. But you never had a real image to compare this back to know if that final printed image, even that final image printed in CMYK, was really accurate or not. So the bottom line with working in the digital realm, where you're creating artwork from scratch on the computer, is that you can never really trust what you're seeing on screen. You can never really trust what you're seeing in print unless you know that those devices are properly calibrated. Calibration is a process that ensures that what you're seeing, either on screen or in print, is an accurate representation of the numerical color values that are stored in that file. It is possible to calibrate a printer, but I'll explain to you in just a few minutes that most illustrators, most artists don't ever do this. But it is something that is done by professional print shops that engage in large amounts of commercial printing. So in order to calibrate a printer, you print what's known as a target image on that printing device. A target image is an image such as what you can see in the bottom right corner of the screen that contains little swatches of colors. And we know what those color values are supposed to be. So in other words, you have a digital file that was purchased from some company. You know what the numerical values of the different colors are supposed to be in that digital file. You print that color image out, and that's your target. You then use a device called a spectrophotometer, and you measure the printed values of those colors. And that's what's happening in that image in the bottom right, is they've printed this target image with all these little swatches of color, and the individual is holding this spectrophotometer device, moving it across the little colored swatches, and it's measuring the actual colors that are printed on that piece of paper. So the spectrophotometer then reads this information back into the computer. There is software that compares what the spectrophotometer is seeing in terms of color with the values that we know those colors are supposed to be. And the computer then generates something called a printer profile, which is essentially something that adjusts the printed image to compensate for any inaccuracies in the print. So in other words, if the print prints with a little bit too much magenta, the printer profile compensates by removing a little bit of magenta every time you go to print a file after that point. So this process of comparing the actual printed values to the known values of those colors, and then building this printer profile that makes little tweaks to the way the printer prints color, this ensures that the colors in every print are then going to match the colors that are stored in a digital file. Now these spectrophotometer systems and the software that comes with them is relatively expensive. Even the inexpensive ones are going to run several $100s, and they go well up into the thousands of dollars for actual professional commercial printing companies. The individual artist typically doesn't need to own one of these things, simply because the artist is usually not the one who is generating the final output of their artwork. For example, in my own work, I don't even own a color printer because there's really no point in me making color prints of my work. I'm sending my digital files off to some of the largest medical and scientific publishers in the world. I'm pretty confident that those publishers are working with printing companies that know what they're doing, that have high quality equipment that has been properly calibrated. So as long as I know that I am sending a good quality digital file with good accurate colors in it, as long as I know I'm sending a good file to my client, I can be pretty sure that the client is going to generate a good quality accurate print from my digital files that I send them. So it's ultimately the client's responsibility, whoever's actually printing the thing, to ensure that they get good quality calibrated print output. The only time I can think of where an individual artist might want to purchase a really high-end printer and calibrate their printer is if the artist is producing limited edition digital prints for sale. I know some natural science illustrators who actually make quite a bit of money by creating natural science illustrations, landscapes, plants, animals, and so forth, and then they sell really high quality prints of their work, really high quality digital prints. So in that case, it may be important for them to own a good printer and actually invest in this sort of printer calibration software. But for most artists, it simply isn't important because you just assume that your client is going to get good quality output. However, it is important that you are sending your client a good file. So you may be relying on your client to generate an accurate print, that they're going to produce a print that accurately matches the colors in the digital file that you send them. But that means that you have to make sure you're sending them a good file that actually has good colors in it. And remember that you're creating these digital images entirely from scratch. The only feedback that you have about what the colors actually look like is what you see on your screen. So I believe it is critical for every professional illustrator to calibrate their monitors to make sure that their monitor is accurately displaying the colors that they are saving into their digital file when they create digital artwork. So monitor calibration is very similar to printer calibration. You purchase some software along with a device known as a colorimeter. The software displays a series of color values on screen, and the colorimeter then measures those colors that are being displayed on screen. And just like with the printer, the software compares the colors that were displayed on screen with what they know the colors were supposed to look like, and it generates this thing called a monitor profile, which is going to make small adjustments to the way the monitor displays color to compensate for any inaccuracies in what it was displaying. So if the monitor is displaying a little bit too much green, the profile then tells the monitor to slightly reduce the amount of green, and this ensures that the colors display accurately. These colorimeters and their software that they come packaged with are quite a bit less expensive than the devices used for calibrating printers. They range in the range between $100 and $200. I think that's a pretty small investment to guarantee that you are producing good colors and sending your clients images with attractive colors and good quality colors, to make sure that you're sending them the colors that you think you're sending them, that you see on your screen. Here are some examples of monitor calibration devices that are currently on the market. Datacolor is my personal choice. I've owned two different Datacolor colorimeters. I had something called a Spider 3 that I purchased many years ago. They no longer sell the software, or they no longer support the software for the Spider 3. So then I purchased something called the Spider 5, obviously a newer model, and that one still works fine with my computers. They no longer sell the Spider 5, even though it still works fine. Now they have the Spider X series of calibration devices. They offer two different models, the Spider X Pro for $169 and the Spider X Elite for $269. The colorimeter device is actually identical between the Pro and the Elite. The only difference is the software that comes with it. And I find that the Spider X Pro is perfectly adequate for the needs of any digital artist. The Spider X Elite is really unnecessary, so there's no reason to spend that extra $100. Pantone, which is another company which is really big in color control, they offer a couple of options as well. There's something called the Color Monkey display for $189, and then something called the i1 Display Pro for $285. Once again, I think the less expensive one is perfectly fine. The more expensive one is really overkill and is not necessary. Now, both of these companies used to sell even cheaper versions of these products. Datacolor used to sell something called the Spider 5, and now I'm drawing a blank. I can't remember what it was called, but it was a budget entry-level model. And Pantone used to sell something called the Pantone Huey, which was a budget entry-level model that was under $100. Fortunately, both companies don't sell those anymore because I don't recommend either of them. Now, monitor calibration might sound like a fairly straightforward process. You load the software, you attach the Spider or the colorimeter device, you hang it on the front of your computer, and I'll demonstrate this process for you a little bit later. You hang the device on your front of your computer monitor, it reads the colors, makes the profile, and you're done. However, the process is a little bit more complicated than that because there are two important choices or two important settings that you have to select before you proceed with the actual calibration step. There's something called the gamma, and there's something called white point or color temperature. And you have to make choices about the values for these two different settings before you can move on with calibration. And personally, I think it's important to understand these two settings so that you can make informed, educated choices about which value to use for gamma and which value to use for white point or color temperature before proceeding with the actual calibration process. So let me explain what gamma is first. To put it very simply, it's a measure of contrast. It's a measure of how contrasty the images are going to appear on your screen. To go into it in a little bit more detail, gamma is a mathematical expression that essentially controls how the RGB values that are stored in your digital file are converted into the voltage that is sent to your computer monitor to actually display the image on screen. So you've got all these ones and zeros representing values of red, green, and blue, but then that has to be translated into voltage that goes to your monitor to actually generate the red, green, and blue light on the screen. And this is not the actual equation, but it's just a close approximation of the equation. The voltage that is sent to your screen is equal to whatever the pixel values are raised to the gamma power. So what that means is if you have a large value of gamma, then any change in pixel value is going to translate into a larger change in voltage. A small value of gamma means that that same change in pixel value translates into a smaller change in voltage. And so essentially what this means is that a low value of gamma is going to give you an image with relatively low contrast because you're going to have smaller differences in the voltage that are sent to the screen and therefore smaller differences in the amount of light that's produced by your monitor. A larger value of gamma is going to give you a more contrasty image because you're going to be having bigger differences in high and low voltages that are sent to the screen. Now, there's some interesting history about how different computer companies chose values of gamma for their different computer systems. When the Apple Macintosh computer was released in 1984, Apple really wanted to create a computer that was designed specifically for desktop publishing. The Mac was released at about the same time as the Apple LaserWriter, which was the first commercially available desktop laser printer. Um, this also coincided approximately with the release of the Linotronics, which was one of the first digital image setters for producing the film that would be put onto or that would be used to create the plates for an offset press. This also coincided with the release of a program called PageMaker, which was the first widely available page layout program. And all of these things were tied together with something called PostScript, which was the first product produced by this little company called Adobe that was brand new in the early 80s. So Apple's goal with the Mac right from the outset was to create this integrated system of computer, software, computer language, the PostScript language sort of running everything behind the scenes, and different kinds of printing devices so that you could design something on a computer screen and then have an exact copy of that image on screen appear on paper. Now, what they found in their testing was that a gamma value of 1.8 allowed them to match what they saw on screen with what they saw on print, so that the image that you saw on your monitor very closely matched the appearance of an image that was printed on their LaserWriter printer. So the Macintosh was designed as a desktop publishing system right from the outset, and every choice about the way that that platform was produced was designed with desktop publishing and graphics in mind. And this was the case right up until very, very recently. When Microsoft saw the Macintosh user interface, the graphical user interface, of course, they began working very quickly on producing their own competing product, which was Windows. Now, Microsoft made some very different decisions when they produced their Windows software. They never intended for Windows to be a desktop publishing platform. It was never meant to be the platform of choice for desktop publishing or for graphics in general. Windows PCs were really designed to be mass consumer market computers, primarily geared towards just average person, and not geared towards a graphic artist, not geared towards people in the printing business, but really geared towards just sort of the mass lay audience, the consumer market. And eventually, they really focused on gaming. And so, even from the very beginning, the PC was designed, or Windows was designed, to simulate the appearance of what you would see on a television broadcast. And a television also has to have a gamma value because you have information that's coming into the television. Back in the old days, it was, came in through an antenna on the roof of your house through a broadcast, a television broadcast. Nowadays, of course, it comes in through your cable, or these days most people don't even have cable anymore. They just have an internet connection, and they just stream things on their television. But you still have to have a gamma value that translates the signal coming in into voltage that appears or makes the image appear on the television screen. So Windows, right from the very beginning, wanted to simulate a television broadcast which has a higher gamma level. It's an inherently higher contrast medium. So for decades, these two different platforms use these two different gamma values. And when you calibrate your software, it's important to choose one or the other of these. Now, an interesting twist happened just a few years ago. Apple finally decided to change the native gamma on their computer systems. They abandoned the old value of 1.8 and instead opted for the Windows setting of a gamma value of 2.2. So Apple intentionally decided to boost the contrastiness, if that's a word, to boost how contrasty their images appeared on screen, because Apple was going for that same sort of mass consumer market focused more heavily on gaming. And I feel that this was kind of an unfortunate decision, because I feel like Apple abandoned their traditional base of people working in the graphics and desktop publishing communities. The other setting that you have to choose before you can actually calibrate your monitor is something known as color temperature or white point. And this is a little difficult to understand. There's a little bit of physics involved, so I'll give it a shot. So there's no such thing as pure neutral white light. Every form of white light actually has a little bit of a color cast to it. The color of light, or the color cast of light, was originally described by Max Planck back in the 1800s. And he produced his theory of what he called the theory of black body radiation. Now, what exactly does that mean? So what Planck theorized was that if you imagine an object that absorbs all light that hits it and reflects nothing, reflects no light, that is a theoretical or a hypothetical black body. Because if an object absorbs all of the light that hits it, and if it reflects nothing, then it's going to appear to be perfectly 100% solid black. Now, it turns out that in reality, there's no such thing as a true black body. There's no object that absorbs all light that hits it. Everything's going to reflect a little bit of light that hits it. So there's no true hypothetical black body. But this was really just sort of a theoretical construct. Now, Planck went on to describe what happens as you heat this black body up to higher temperatures. Eventually, that black body is going to begin to glow. It's going to begin to emit light. And it turns out that this theory of black body radiation was the basis for the invention of the light bulb. The idea that you could pass an electrical current through a metal filament, and that metal filament would begin to heat up, and as it heated up, it would begin to glow and emit light. The temperature of this hypothetical black body is expressed in units of Kelvin on the Kelvin temperature scale, where 0 degrees Kelvin is what we refer to as absolute zero. It's the temperature at which all matter stops moving. A black body that is heated up to a temperature of 200 Kelvin begins to glow a dull orange color, similar to the light that is emitted by a candle. If you continue to heat that black body up to a little bit higher temperature, up to about 2500 Kelvin, you get a slightly yellowish light. It begins to emit a slightly yellowish light, which is the same color of light that's emitted by a typical incandescent light bulb. At much higher temperatures of say 5000 to 5500 Kelvin, this is the color of most lighting in a typical office workspace. It's also the color of daylight when viewed at the level of the horizon. At an even higher temperature, that black body would radiate light with a slight bluish tint to it, which is like daylight in Rochester, where it's constantly overcast. That gray overcast almost gives the light a sort of a bluish cast to it. And then as you continue to increase the temperature of the black body, it glows an even brighter blue, a more vivid blue. And this is kind of like the blue glow that you see from television. Um, if you've ever driven past somebody's house at night and they have the television on, you can almost always tell because you see that distinctive blue glow uh, radiating out from the windows of the house. You don't realize just how blue a television broadcast is until you see that blue glow shining out of somebody's house, out of their living room at night. Now, you may have noticed that the colors of light at different temperatures are kind of opposite the way we normally think of color and temperature. As artists, we're trained to think of colors like yellow and orange as being warm colors and blue as being a cool color. But in Planck's theory of blackbody radiation, it's just the opposite. When things just begin to start to glow at very cool temperatures, they glow orange, and as you increase the temperature, they glow more yellow, and eventually they glow blue. And you can actually confirm this if you've ever looked at a gas flame. If you've ever looked at the flame on, say, a gas stove, the hottest part of the flame is at the center, and it glows blue. And then towards the outside of the flame, that blue light transitions to more of a yellow and then eventually to orange at the outermost part of that gas flame where it's the coolest. So you can actually confirm that just by looking at a typical flame on a gas stove. Now, when computer systems are produced, the computer also has to specify kind of a default setting for the color of white light, the appearance of white light on that computer monitor. And just as with the gamma setting, there's some history here related to the development of different computer platforms in the later part of the 20th century. When Apple released the Mac in 1984, in addition to choosing a gamma value of 1.8, they also decided that the color temperature, the native color temperature for the appearance of white on the Mac should be a color temperature of 5000 K. This is also sometimes known as D50. And they chose this because they felt that that color temperature of 5000 K simulated reading conditions in a typical office environment. When Windows was released, in addition to choosing a gamma value of 2.2, they opted for a color temperature of 6500 Kelvin, also known as D65, because this simulates the appearance of a television broadcast. It has a much more noticeably blue cast to it than the 5000 K temperature of the Mac screen. This was true for a few decades. But then just a few years ago, at the same time that Apple changed their native gamma setting from 1.8 to 2.2, Apple also changed their native white point from D50 to D65. So now, essentially, all computers that are sold are coming with default settings of 2.2 gamma and D65 for the white point or color temperature. Now, even though these computers are now all shipping with the same standards of 2.2 gamma and D65, it is possible to go into the computer system and change these settings. It's also possible during the calibration process to change these settings from one to another. So the question then becomes, when you calibrate your monitor, which of these settings do you choose? Do you stick with the standard 2.2 gamma and D65, or would there be a reason to possibly change to other settings? If you read articles online or search YouTube videos, you'll find that most experts these days recommend sticking with the standard 2.2 gamma and D65 that all computers are shipping with these days. And they have some reasons for this, but frankly, I don't really necessarily agree with their reasoning. Basically, I feel like they're just sort of throwing their hands up and saying, well, everybody's computers are set to 2.2 gamma and D65, so you should too. Um, and I believe the other reason that they recommend these settings is that they want people to calibrate their monitors for the creation of images for the web, the creation of graphics for gaming, and also for the streaming of digital video. So they are recommending the 2.2 gamma and D65 because these are the preferred settings to simulate the appearance of images on television. And since most people are using their computers these days for surfing the web, for gaming, for streaming video, and so forth, that you should stick with those settings. Now, I have a little bit of a different opinion on this matter. And I think I'm in a small minority, but let me give you my reasoning. I recommend that you continue to set your computer to a gamma setting of 1.8 and D50, the old Mac standards. Why is that? First of all, even if you set your gamma to 2.2 and your white point to D65 to match the way most people have their computers set up, you still have no control over what the end user is seeing on their other end. So in other words, if you set your computer to 2.2 gamma and D65 and you create artwork that's meant to be put up on the web or animations or streaming videos and so forth, you still have no idea what that's actually going to look like on the end user's computer, because most people across the world own inexpensive monitors and almost nobody actually calibrates their monitors. So what they're seeing could be all over the place. No matter how much you try to control what they see, you really don't have any control over what they see. They're going to see all sorts of crazy colors because their monitors are all over the place. They're inexpensive. They're not calibrated at all. So you can't control that. So I don't really see the point in you trying to match the 2.2 gamma and D65 of other people's computers, because it's still not going to ensure that the colors you produce are the colors that the end user sees. They're still going to see something very different from the colors you produce. So you simply can't control that. On the other hand, if you calibrate your monitor to match print output, and assuming that you are sending your digital files to clients who are using properly calibrated printing devices, then that helps ensure that the artwork you create on screen really is going to look the same as the printed output that your clients are generating. So if you produce any work that's intended for print, you actually can control how those prints are going to look at the end. So you want the colors that you see on your monitor to match the colors of the printed output. And again, this assumes that your client is going to use properly calibrated printing equipment, which should be the case if you're sending your digital files to an actual commercial publisher, a journal publisher, a textbook publisher, so forth. So for this reason, I recommend sticking with the old Mac settings of 1.8 gamma and D50, because those settings are set up to ensure that what you see on screen matches what comes out in print. And like I said, you can't control how other people, other mass users, are going to see how your work looks on, when they look at it on the internet or on streaming video. So we're not going to worry about, trying to control what they see. Now, for this reason, I mentioned earlier when I was describing some of the colorimeter devices that are on the market, I mentioned that both ColorVision and, Datacolor and Pantone produced or used to produce some inexpensive budget entry-level calibration devices. And the reason that I recommend avoiding the really cheap ones like the ColorMonkey Smile or the Pantone Huey I think the data color one is called the Spider Express. Uh, these things have a fixed set of settings. They have a fixed gamma of 2.2 and a fixed white point of D65. They don't let you change them. Whereas the mid-range devices like the Datacolor Spider X Pro and the mid-range Pantone device, the Color Monkey, I believe it's, what was it, the Color Monkey Design or something like that. These things let you actually control the gamma and white point settings. Hey, welcome back. Now I'm going to begin to demonstrate the process of actually calibrating your monitor using the Datacolor Spider 5 Pro. Here is the actual gizmo, the Spider 5 Pro. It has its USB cable, which is already plugged into the computer. And if we look at the device itself, it actually separates into two pieces. This piece over here has a couple of functions. First of all, it acts as a lens cover to protect the sensitive optics inside the calibration device. Its other function is to serve as a counterweight, because we're actually going to hang this thing over the top of the computer so that the colorimeter part is actually pressed right up against the front of the screen to measure the colors, and the other piece then acts as this counterweight to counterbalance that weight. So let me open up the actual calibration software and begin to actually demonstrate how this works. So I'm going to quit out of here. And here is the Spider 5 Pro software. I'm going to click OK. And it gives us a little checklist of things to consider before we actually begin the calibration process. First of all, you have to make sure that the monitor has warmed up. I mentioned earlier that monitors actually look a little bit differently when you first turn them on as compared to after they've warmed up for half an hour or more. So it wants to make sure that you've let your monitor warm up for at least 30 minutes. You want to make sure that you don't have any strong direct lighting shining right onto your monitor surface. If your monitor has controls that allow you to reset back to the factory defaults, they recommend that you do that. My monitor doesn't have that capability. And then finally, they ask you to connect the Spider to a USB port, which I've already done. So let's proceed to the next step. Do you have a desktop or a laptop computer? I'm calibrating my iMac, so it's a desktop computer. And then they ask you to select the manufacturer and the specific model of computer or monitor. They ask what kind of controls do you have on the outside of the monitor. I have brightness controls, which I can set right on my keyboard. I don't have presets for changing the color temperature in units of Kelvin, such as 5000 or 6500 K. So I'm just going to leave that unchecked. And now is where I get to make the important decisions about my gamma and white point settings. I'm going to change the gamma from their recommended default setting of 2.2. I'm going to change that to 1.8. And I'm going to change the white point or color temperature setting from 6500K or D65, change that to 5000K or D50. Now I also have some other options. I could adjust the brightness settings on my monitor, and I could also check for ambient lighting in the room, because the lighting in the room can influence the way colors appear on screen. I'm going to skip that step for now, but be aware that sometimes that can be an important thing to do. So now they want me to actually hang the Spider device on the front of the computer using that counterweight in the back. And frequently it's necessary to tilt the screen back so that the colorimeter device hangs in the correct position on the front of the monitor. and so it lays flat up against the front of the screen. So I've got it in the correct position. I'm going to click Next. And the calibration process begins. And what it's doing is it's displaying a series of different color values, white and black, and eventually it's going to go through a set of red, green, and blue color swatches. This can take a little while. Hopefully you can see in the video that it is displaying different shades of red, starting out with just pure black, just the complete absence of color, but then gradually turning up the red values. And eventually we'll get all the way up to a value of 255 red, which is the maximum intensity of red. And then it'll do the same thing for green and for blue. And eventually it'll also cycle through some neutral grays. If I can figure out how to do this in the monitor recording software, the software that I'm using to record the video, I'm going to see if I can speed up this process once I actually complete the final video. I can remove the device, and it's asking me to name a profile. You may remember earlier I mentioned that when the calibration process is complete, it builds something called a profile, which is going to make adjustments to the way colors actually display on your monitor. What a lot of people do when they create these profiles is they actually give them a date. So I'm going to enter in today's date so that I know when this calibration profile was actually created. And I can even set a reminder for myself to calibrate or to recalibrate the monitor periodically. And you can see that I could calibrate as often as every day or as infrequently as every 6 months. Most professionals would recommend that you do this periodically, at least every few months, if not more frequently. So I'm going to leave the reminder at 3 months, and I know that when 3 months is up, I'll get these little warnings that'll pop up on my computer. And I click Save. Now this is a really interesting feature of the calibration software. It lets you compare what your monitor looks like right now with the calibration settings that I've chosen with what it looked like prior to the calibration. Now, I intentionally went into my system preferences and set the calibration settings to sort of an uncalibrated default setting so that when I actually did the calibration, you'd actually see a noticeable difference between the calibrated view and sort of the uncalibrated default settings. So right now what you're seeing is the calibrated view, and you see all these little color swatches or all these little images on here, and I can switch to show you the uncalibrated view, and hopefully this actually shows up in the video. So there's the uncalibrated view, and you might notice just how much bluer the screen is because this was using the default D65 setting. Whereas when I calibrated, and let me switch back to the new calibrated setting, this is using the 5000K setting, which has a noticeably warmer cast. And personally, I think that the skin tones look a lot better in when calibrating with the 5000 Kelvin, the warmer tint to all of the colors. I believe I can click on individual images here to enlarge some of them. Here's some different skin tones, but let me just pull up this one woman. And again, I'm looking at the calibrated view using 5000 Kelvin, and I feel like the skin tones look very natural and very warm. When I switch to the uncalibrated view using 6500 Kelvin, there's a much more noticeable bluish tint to the skin. I think the skin almost takes on a greenish appearance because the peach or yellow tones of the skin mix with that bluish cast to create almost a greenish look. So if nothing else, I think you can see just how much the color settings, the color temperature settings influence what you're seeing on screen. So here's, again, 5000 Kelvin, nice warm skin tones, 6500 Kelvin with the noticeable bluish cast. I'm curious what the blue sky is going to look like, because blue sky is something that we all sort of recognize. We recognize when the color of a sky looks normal. So here it is uncalibrated, and so 6500, and there it is in the calibrated view. And you know, there's a difference, although I'm not sure that one is necessarily preferable to another. We could look at a grayscale image, because grays will have a noticeable color cast to them. You can have warm grays that have warm tones. You can have cool grays that have cool tones. And right now we're looking at the calibrated view, which I think looks perfectly fine. We switch to the uncalibrated 6500 Kelvin setting, and I think the blues immediately take on, or excuse me, the grays take on a noticeable blue cast to them. So I'm going to go ahead and click Next, which will complete the calibration process.